All right, so hello and welcome everyone to the third installment of the Open Source Drilling Community's technical series. So this afternoon, depending where you are on the planet, we'll be hearing a little bit about stick-slip vibration. So how do you model it, how do you estimate it, then also how do you avoid it? And we're going to have two speakers today. So Jean Auriol from the Université Paris-Saclay and Florent de Meglio from Mines ParisTech. As I will do a quick point out, the three of us have been working together on aspects of this over the past couple of years. So there's some really cool results and some really cool opportunities that we'll be talking about. So with that, I'll hand it over.
Thank you very much, Roman. I was actually going to say that most of the work that I'm going to be talking about in this presentation is in collaboration with Roman and with Ulf Jakob Arsnes, who is in Norway. And actually, some of the stuff I'll be mentioning is exclusively Roman and Ulf's work. I just stole it for the presentation. The other thing is, if you have any question at any point, please don't hesitate, interrupt me. And I'm sure that Jean has the same rule. Please say it now, Jean, if it's not the case.
It's perfect for me.
So, okay, so we will be talking about stick-slip vibrations, and I will be mostly talking about modeling and estimation, and then Jean will talk a little bit about how we can avoid, how we design control methods to avoid stick-slip at startup. So with that, okay, so I use these slides a lot, so I had a short introduction on drilling, but I'm not sure this is really necessary. The important thing here is that we're going to focus on the torsional dynamics. Mostly in this talk, we'll be talking about the torsional dynamics. And so throughout the presentation, torque will be denoted tau and angular velocity omega. A first aspect of what we're going to do is we're going to assume that there are three main components here. Whatever's happening at the surface of the drill rig, which includes a rotating mechanism, either a rotator table or a top drive. And we're going to be using mostly sensors that are located at the surface. So whenever you will see a bottom hole sensor here, it will be used to evaluate the capacity of the models to replicate the behaviors or the accuracy of our estimators. But the bottom hole sensor, we try to avoid having to use them online on the rig. And then we will assume that the drill string and BHA are two separate components, with the BHA being a little heavier and larger. I'm assuming that most of you know about stick-slip. Just to be sure that we're on the same page here, these are unwanted torsional oscillations with a cycle of sticking and slipping. So if you look at the bottom plot on the bottom left here, you have a plot of the downhole RPM with phases of stick where the RPM is close to 0, and then phases where the RPM, the bit accelerates a lot. This is obviously a distributed phenomenon, so you have inhomogeneous velocities up and down the BHA and the drill string. And the period of these oscillations is typically 3 to 10 seconds. And this is, an undesirable behavior, which causes wear and tear on the equipment and reduces the effectiveness of the slipping, so decreases the ROP. And one thing that's important is that there's a pretty clear signature on the top at the surface, and you see the torque build up and then drop down when the system experiences stick slip. Okay, so if Okay, so one thing that's important about these oscillations is that they are not what we would call free oscillations. So let's assume that your drill string is at rest here, so no rotation, and then you hit it with a hammer, or you just impose some kind of torsional disturbance at the bottom here. What will happen is that you will get some oscillations that will eventually die out because no energy is entering the system, right? Stick slip is a different animal, I would say. And to get stick slip, you need some kind of instability to be present in the dynamics of the system. And there's mainly two phenomena that can contribute to this instability. The first one is what is called in the literature the regenerative effect, and that comes from the bit-rock interaction law. And if you look at the RPM at the bit or at the table, the signature will look something like what's on the left, with oscillations that progressively grow out of control. And the second potential cause for stick slip is what's called the velocity weakening effect that comes from the side forces. So I'll be briefly talking about the regenerative effect before I focus on the velocity weakening effect. Most of the talk we'll be talking about the second aspect, but just for completeness, the regenerative effect, it comes from the coupling between the axial and the torsional dynamics. It was a well-known phenomenon, well identified for cutting processes, and then in the 90s it was identified and proposed as a model for to be the root cause for stick slip in drilling. And again, like I said, it really comes from a mix between a coupling between the axial and the torsional dynamics. Okay, but sorry, again, this comes from the interaction between the drill bit and the rock that you're cutting. But it so happens that you can get stick slip while you're off bottom. And so if you are off bottom, then the bit rock interaction cannot be the cause for stick slip. So there must be something else. And this something else is, at least sometimes, something that's called the velocity weakening effect of side forces. So what do we call side forces? Well, it's just the interaction between the drill string now and walls of the borehole. And what we mean by velocity weakening is that as the rotational velocity of your drill string increases, these side forces may decrease. Okay, so you have less force with increased velocity. So, okay, the goal of the presentation here is, first of all, to show a model that accurately replicates off-bottom stick slip. And why do we want a model that replicates it? Mostly because we want to try and monitor the system. So propose algorithms that are able in real time to estimate, let's say, downhole RPM from surface sensors only, and also try to estimate some kind of friction factor. So something that gives us information about the friction forces along the drill strings. Once we do that, we'll also use the model to try and discuss mitigation techniques. And as I said, this will be mostly from Jean. And then we'll go on and talk about perspectives. Okay, so I said that we wanted to model stick slip, and one of the important things to do when you want to model a behavior is to look at the data. And one thing about the stick slip data that you encounter in the field is that it has a very wide frequency spectrum. So what you see here are spectrograms. So on the x-axis, you have frequency, and on the y-axis, you have time. And the more yellow you get, that you have on the spectrogram, the higher energy is present in the system at a given time and for a given frequency. And what you see here is that you have energy in the low frequency, so around 1 hertz, but there's actually still a lot of frequency around 5 and even around 6-7 hertz. And if you look at the torque dynamics, or the spectrogram of the torque in the middle, you have things that are much higher, around the range of 10 to 15 hertz, right? And so this motivates the need for models that are relatively accurate in the high frequency. And that means that you need to take into account the distributed nature of the model. The reason for that is that if you use lumped models, as frequency gets higher, the approximations get worse and worse, right? So what I've shown here is a Bode plot of the linearized model around a certain equilibrium, and if you look at the frequency response of an infinite dimensional model, so a model with an extremely large number of discretization points, you have the blue curve. So on the top, it's the magnitude of the frequency response. On the bottom, it's the phase. And in black are several lumped model approximations with an increasing number of lumps, if you will, of sections. And so you see that even if you divide your drill string into, let's say, 5 control volumes, you still lose quite a lot of the model response, and you very quickly have a deviation from the distributed dynamics of the model. So for that reason, Roman and Ulf, as I mentioned earlier, derived a model based on the following assumptions. So there's quite a lot of them. First of all, like I said before, because we're interested in stick slip, we're going to assume that the torsional motion of the drill string is the dominating dynamic behavior. This is also possible because, as is written on the bottom here, we will consider the bit to be off bottom. So again, the coupling between the actual and torsional dynamics is not relevant here. So we'll discard the actual dynamics here. As we will see later, we will basically neglect the Strebeck effect. So assume that the changing from static to dynamic friction is a jump. And the effect of cuttings or the pressure from the drilling fluid is basically assumed to be negligible. So where does that take us? A relatively simple model that you get by just simply writing the mass and momentum conservation laws for the distributed drill string. As I mentioned earlier, tau is the torque along the drill string, omega is the rotational velocity, gi is the inertia, g the Young's modulus, and rho is the density of the pipes. And so the mass and momentum conservation laws give you basically something that looks like a wave equation. So you have 2 equations here. X is the abscissa along the drill string, and the index I is used to denote the fact that we have 2 different equations. One is for the drill pipes, and the other one for the BHA, basically. Okay, and you see here that in the second equation, which is the momentum conservation law, you have a term on the right-hand side, which is basically the external forces. And we're going to talk a little bit about these forces, which are going to be mainly Coulomb and viscous friction from the contact with the borehole. Along with these equations, you have equations that at the junction between the pipes and the collars tell you that you have continuity of the states. And you also have some boundary conditions, which tell you what's happening at the top and at the bottom of the drill string. At the top, we assume that we have an actuated top drive with a motor torque tau m. And so you have ITD here, which is the inertia of the top drive. And so this equation here tells you that basically the motor actuates the top drive. And then there is some torque that is transmitted to the drill string. And like I said, we assume that the bit is off bottom. So we assume that there is no contact between the bit and the rock. So the torque at the bottom of the well is assumed to be zero. And as we will see by comparing it to field data, this model is able to replicate the behavior of a drill string at the startup of a drilling operation fairly well. Okay, so let's talk a little bit about these side forces, the source term S in the momentum equation. Like I said, it's assumed to be only composed of friction side forces. And so the term S looks a little bit something like this. So let me zoom in a little bit. So how should we read the diagram that's on the top here? Well, you see that if your velocity omega is outside of the gray area, then the value of S is simply given by the red curve, and it increases with linearly with omega. So this is basically just viscous friction. What's more interesting is what happens when omega gets small. And what you have here is what you call a differential inclusion. The idea is that within the gray zone, the value of S is basically whatever is needed to maintain the drill string or the drill string at this precise location as fixed, as long as the torque is smaller than the value FC, which is the maximum friction force, right? So what happens is if you start, let's say, at zero velocity and you progressively increase the torque, well, you will basically live on the y-axis at the beginning. So you will progressively, let's say you're at a zero torque, right? And so you're right in the middle of that diagram, and then you progressively increase torque. The velocity will remain zero until the torque exceeds the value FC. And then at that point, the velocity will jump to the red curve as the system starts accelerating and the velocity is not zero anymore. Okay, so this is basically all that diagram says, and the equations below. Like I said, the jump from a zero velocity to a non-zero velocity is assumed to be instantaneous. Usually, you could have a Strybeck curve here in that region, but it's neglected here. Yeah, and the other thing is that sorry, there are several parameters here. The static friction coefficient, which is μs, and the kinematic friction coefficient, which are usually poorly known. And actually, one of our goals here will be to estimate them from field data. So that's one thing. The other thing is that in these equations for the friction, the inclination of the drill string at each location is a relatively important parameter, as if the well is vertical, then you have barely no friction, whereas if the well is horizontal, you will assume that you have a larger impact of friction on the dynamics. Is there any question on this friction model, or is this, yeah, like I said, if there's anything, please interrupt me.
Oh, I have so many questions, but I'm going to wait until you finish out.
Okay.
I have lots of things we'll ask about later.
Okay, great. Okay, so this comparison with field data is taken from a paper by Roman and Ulf. Correct me if I'm wrong, Roman, but it required quite a lot of manual tuning to get this result. So what you see on the left here is the RPM on the top, the torque in the bottom, and I guess the most important variable to look at is the yellow curve here, which is the bottom hole velocity. So the bottom hole rotational velocity, and it has to be compared with the dotted line in black, which are the min and max value recorded on the field. And as you see, there's a very good agreement here between what's happening at the between the model and the field data. And so this is just running the model with this is just an let's say open loop simulation of the model compared with field data after some calibration. Again, another comparison at a deeper location, another startup where again you see that this combination of building up the motor torque and then the motor torque dropping down because of the stick slip phenomenon. Again, very good agreement between model and the field data. Okay, so how do we want to use this this model? Well, one thing we would like to do is to monitor in real time the angular velocity and the torque. And we would like to do that even when we don't have bottom hole sensors. And so the question we ask ourselves is, how can you use the model in combination with topside sensor information to try and estimate what's happening in real time at the bottom? So that's one thing we'd like to do. If possible, we'd like to also try and estimate the static and kinematic friction factors that appear in the model. And finally, and this will be the second part of the talk, Jean will tell a little bit about how to regulate the velocity at the startup of a drilling operation to try and avoid entering this limit cycle by designing smart controls at the top. Okay, so to try and estimate what's happening at the bottom only from surface data, what we use is what we call an observer in systems and control. And like I said, it's a combination of the model and the real-time data. So this is our model, and what we're going to assume is that we have a measurement, and this measurement is the topside velocity. So we need a topside velocity sensor for everything that I'm going to mention later. And we also need to know the value of the torque at the bottom so that we can inject that directly in the model. And so with these two surface measurements, what we want to do is basically feed these measurements somehow to the observer so that it gives us some estimation of all the states. So all of the distributed states, tau and omega, all along the drill string. And so we do that by modifying the model as is written below. So let's take just a little bit of time to understand what's happening here. What you see on the bottom is what we call the observer dynamics. So this is the equations that we have to solve in real time to get an estimate of the torque and the velocity at any given location. So we don't actually simulate the model as is written on the top. What we do is we simulate the corrected version that is on the bottom. And this corrected version has the measurement y that is coming into the equation directly, changing the dynamics, if you want. And it's changing in the dynamics in a way that is determined by the coefficient p tau of x here, p omega and p1. And so basically my job as a researcher in systems and control is to try and find smart ways to design p tau and p omega and p1 such that the estimates given by the model on the bottom match the actual velocity and torque on the system. And so I'm not going to go into the details of how these are designed. This is based on an analysis of the convergence properties of the equations. But the important thing is what you see here really is you mix the model. So you see the equations on the left-hand side and the S here, they're really a copy of the original dynamics, right? The only thing that I've done is to add these correction terms here. So this is really a way to mix the information that comes from my sensor and the information that comes from the model. What you can sort of infer is that, okay, if p tau, let's say if the coefficients p are very small, in a way that means that I'm not correcting my model a lot, and that means I trust my model very well. On the contrary, if I have very large values of p tau, it means that I'm actively trying to modify the physics of my system so that this difference between my measurement and the estimate given by my model of what the measurement should be are as close to each other as possible. Okay, and so this is not the only thing that we estimate. We, like I said, we also estimate the parameters that appear in the friction law. So yeah, sorry, actually this comes from older slides. So if you will, you can discard the first equation. What's really important is these two equations at the bottom here. You remember that mu s and mu k were my static and kinematic friction factors, and what we do here is we build estimates of these two that we continuously update over time using a differential equation for mu s and for mu k. And this E here is the difference between the topside velocity as estimated by my model and the current measurement. So it's the E is exactly this term that is in brackets right here. So most of these ideas basically consists in just comparing how fast my model thinks it's spinning, how fast the actual measurement is spinning, and try to correct the estimation of the kinematic and static friction factors based on this. And these conditions here, they're pretty straightforward. They basically say that if I think that I'm in a stick phase, then I'm only going to update my static coefficient. If I think that I am in a slip phase, then I will update my kinematic friction coefficient. Okay, so in the design of the coefficients p tau, p omega, etc., we are guided by rigorous proofs of convergence of these estimators in certain simplified conditions, whereas the static and kinematic friction estimators are much more heuristic, and so there's some more theoretical work to be done here to guarantee convergence, and we haven't succeeded so far, but we have tested these algorithms against simulated and experimental data. One of the good things, so sorry, so here on the left, you have, so sorry, this is simulated data, right? So we we take a model, and then we test our observer on this model. There is a small difference between the two models, the one used for observer design and the one used for the simulation here. So the one that acts as if it were the plant. The difference is that the drill colors for the observer design are just modeled as a single lumped approximation, whereas in the simulation model, they are still fully distributed, which is the reason why when we compare the bottom RPM on the bottom left plot here, we don't have perfect agreement between the observer design, but we have relatively good agreement. And as you see on the right, we are able to perfectly reconstruct the static and dynamical friction coefficients over time, starting from an initial guess, which is completely off. And then we tested the same estimation strategy on field data. And what you see here on the left is various estimation. So these are various estimates where we've just started the estimates from different initial conditions every time, just to check that we were always converging to the same estimate of the static and kinematic friction term. And it was the case. And as you can see on the right, the downhole RPM is after a transient where the frequency is a little bit off, is then properly estimated. Okay, so one important thing about these results is that we had very good measurements available, 20 Hertz. The quality of the estimation significantly deteriorates when the frequency of the sensors decrease. But around 1 Hertz, we still have acceptable results. Below 1 Hertz, we lose most of the performance. Again, Roman, correct me if I'm wrong. Okay, so I see that I will go, there was another method for estimating these parameters, but I will not go into the details. And actually, I will let Jean now tell you a little bit about how we use the model for control.
Thank you, Florent. I'm just going to share my screen so that I can move the slides from my computer. So just, okay. There I go. Can you all see my screen?
Yep.
Okay, perfect. So let's go back where you stopped. Okay, so Florent, thank you for your part, Florent. So Florent showed you
John, we can see your full PDF window. So can you go to full screen view?
Yes, I mean, okay.
Okay, we see like, there we go. Much better.
Okay, perfect. Okay. So the problem is that the PDF is not on the same screen, so I won't look at the camera. So don't think it's rude. But, so yeah, thank you. So Florent showed you the model we used for the drilling device, and the observer we derived actually that mostly Roman, Florent, and Ulf derived. I'm now going to talk about the controllers that we can obtain for this kind of systems. So, and I will show you how we can use these measurements to improve the control load. So usually we can act on the orientation. We would like to control the DHA velocity, but the problem is that we have for a majority of drilling rigs in the field, the actuation is done through electric top drives, so using some kind of control input. So we have the actuation dynamics at the top. So the top drive angular velocity is subject to the motor torque. And so the objective is to find the correct control input for the motor torque using the available measurements so the top drive angular measurements. And the objective is to have to control the downhole angular velocity, and we want to reach a given reference. So we want to have omega that reaches omega ref, and to do so, we can only act at the top. So our job as control engineers is to find the correct control input, so the function C of S, so that we can have this control objective. Sorry. Okay, so to do so, it might be convenient to perform an analysis in the Laplace domain. So we can just take the Laplace transform of the top drive angular velocity, and basically taking a derivative corresponds to multiplication by a variable f. And the top drive control will be given as a transfer function, so C of S times omega TD. And we want to find C of S, which is the control input. You have the expression of the top drive impedance and of the wave reflection, where zeta P is the pipe impedance. So I'm not going to spend time on that because otherwise I would be running out of time. But basically, you have a classical stick slip mitigation strategy, which is given by the following scheme. You have several parts on the scheme, and industrial available top drive speed control are usually based on either the whole scheme or only a part of the scheme. So two types of stick slip mitigation controllers have been widely developed, and in particular, you have the soft torque and soft speed systems and the newer Z-torque systems. So these controllers have been proved to be more efficient compared to simple stiff PI controllers, and they have been improved by completing them by a feed-forward action. And this is what I'm going to show. So you have the first part, which corresponds to the stiff speed control law. Basically, it's a kind of PI control law where you have some gains, Kp and Ki, that are used so that the top drive RPM track the set points. So it's a basic control laws, which is based on classical PI controllers that are used in the industry. Then you have the soft torque, soft speed. The two products, soft torque and shell soft torque. For this solution, the objective is to reduce the reflection coefficient at the top drive in a certain key of frequency range. So some improvements have then been done to obtain the Z-torque controller. So in the Z-torque controller, in this new solution, the reflection coefficient at the top is minimized for a wider range of frequencies by measuring the torque between the drill string and top drive. And the feedback controller is used to artificially have the top drive that match the impedance of the drill pipe. So this is this new part of the block diagram. And so basically at high frequencies, you have the top drive, which is controlled to cancel reflection. And at low frequencies, you follow the given set point. The problem with V-torque is that, of course, it might be better, but it's at a cost. You have high instantaneous torque, and you may have a slower response. So I'm just going to show you stability map comparison when the bit is off bottom. So we want to regulate the downhole velocity. And we have different cases. And we compare the stiff controller, so basically just a simple PI controller, the soft torque, and the V-torque. So you can see that Z-torque is lower here. But at the end, here the reference velocity is around 60 RPM. And you can see that they all manage to reach this reference velocity, but you have some oscillation for the stiff controllers, whereas the soft controllers quickly converge to the right value, and the Z-torque does not have any oscillation, but it's much slower. And here you have the torque. However, you have also some cases where the stiff controller and even the soft torque controller do not manage to reach the reference, and where you still have the stick slip phenomenon. In particular, when you have some strong orientation, because in that case, you have stronger stick slip effects, and this is why they do not manage to stabilize the system. Here you can see that the Z-torque does not have any oscillation and avoids stick slip and manages to reach a given set point, which is still 60 RPM. However, you can see that you have a high instantaneous torque because it reaches 30 kilonewton meter. We have put a saturation because we want it to be realistic, and so put a saturation on your actuation, because with your actuation you cannot reach any arbitrary high value. Okay, so the question we have when we see this plot is, can we do better? Because basically these three control algorithms are efficient ones are simpler because they are kind of PI, improved PI controllers, but yeah, they are kind of simple, but maybe we can do better using some recent developments that have been obtained for distributed parameter systems. So this is the question we want to solve. Can we improve the performance of the closed loop system? And actually there is a simple thing that we can do, which is to combine one of the previous strategies, so either the soft torque or the Z torque, with a feed-forward component. So I've rewritten here the different slides, the different equation in these slides, and so you can see that it's the same as before with the inclusion. For the control design, I will neglect the term KT because actually it's really small and the effect is not really important. So it can be neglected compared to the effect of the Coulomb friction F. And you can see something which is important is that as it's an inclusion differential equation, if omega is large enough, the function S actually does not depend on time, which means that it's a kind of constant, distributed in space, but constant in time disturbance. And this disturbance can be compensated using appropriate compensation procedures. So we will do a kind of switching mode strategy. First, we will send enough energy to release the BHA so that we are in a kind of a linear mode where the disturbance term is constant, and we can compensate for it and do some tracking to reach the control objective. Of course, we need to guarantee that we do not go back to the bad mode. Otherwise, we will have some nonlinear dynamics and we are screwed. So in the first, for the moment, I will assume that D is equal to 0. And I won't present disturbance compensation procedure. I'm just going to present a feed-forward one. From this equation, you can obtain the transfer function of the system. You can basically take the Laplace transform of this equation and do some algebraic computation to find the transfer function between the top drive velocity and the downhole velocity. And you have D of S, which is a transfer function that depends on the different physical parameters and on the delay, which is induced by the transport phenomenon. You can do the same to have the transfer function between the motor torque and the top drive angular velocity. And now you can combine the Z-torque procedure with the feed-forward control law. I mean, you want the downhole velocity to reach omega set point. So it's sorry, you want the downhole velocity to reach omega f. So if you use this equation and you replace omega downhole by omega f, then it gives you the corresponding set points, the corresponding top drive velocity. So you know the top drive velocity you want to reach, and then you can simply find the corresponding motor torque to reach this velocity. And so this gives you the reference plus a correction terms, which is tau mf due to the feed-forward component. And this gives you the new control law, which is not just the Z-torque controller, but the Z-torque plus a feed-forward controller, so that you reach a good reference. Once, if you have the disturbance D, then you need to add a third term, which will be the disturbance compensation term, to get rid of this disturbance. But as this disturbance is constant in time, it's kind of easy to deal with it using a similar procedure. Another approach is an MID procedure. So these two procedures, the one I'm going to show you, are kind of theoretical results. They need to be compared in terms of performance, of course, and on computational time, but there are possible strategies that can be followed for the next step. So basically, as we want to control what we have at the bottom of the well, we can write the equation satisfied by the downhole velocity and using the transfer function, find a link with the actuation. And basically, we get a time delay equation between our actuator and what we want to control. The function L is what we call a quasi-polynomial function. So it's a quasi-polynomial function, which means that the P of S is a polynomial and Q of S is a polynomial, except that you have a delay. So you have an exponential, and so it's a quasi-polynomial function. The goal of the MID controller is to directly design tau m as a PID control law of omega dh to guarantee the placement of the dominant root. So basically, instead of doing pole placements as you do with a PI controller at the top, you do it for the downhole state, the one you want to control. The problem is that the computation are more complex, and you may need some derivative of the state, and so some filtering aspects. Finally, the last class of controller I want to present is what the recursive interconnected framework. Basically, your pipe is composed of different subsystems. ODE at the top, some PDEs, actually one big PDE, or if you have different sections, different type of pipes, several PDEs which are interconnected, and one ODE at the bottom, which corresponds to the BHA. And so for each system, you can define an input for this system, which corresponds to the output of the previous system, and an output for this subsystem. And so for each subsystem, you want to find the virtual inputs that would stabilize it and guarantee that the output of this subsystem converges towards the virtual input of the next subsystem. So basically, you start from the bottom, you find what would be the good input for this ODE, then you go to the PDE port, what would be the good input to stabilize this PDE and have the correct output, etc., etc. So if you do it for ODE, for instance, this is an ODE. It gives you stabilize it. You can it is sufficient to choose Vn+1, so the last one, defined like that. Then you can iterate for the PD subsystem. You iterate, and you get at the end the top drive torque, which is defined as a function of V1, and V1 is defined as a function of V2, V2 is defined as a function of V3, etc., etc. And the last one is directly defined as a function of omega ref and omega dh. The problem with this control strategy is that it's really efficient. It can be used to compensate for the disturbance. However, it requires prediction of the states, and it requires computation and filtering to get strictly proper control and avoid some robustness issues. So it's a control law that presents really good performance, but that might not be satisfying from implementation point of view. So we will compare the different controllers on different test cases. In the first test case, you have an almost vertical way, and I plotted the RPM and velocity and the torque. So here you have for the torque, classical torque. So you still reach the reference, but you have oscillations, and the same for the torque. If you use the feed-forward component, you can see that you have almost no oscillation. You just have a small overshoot. You have really small oscillation for the torque, but it is acceptable. And for the MID and recursive algorithm, you can see that the recursive algorithm is almost perfect, no oscillation at all. And the MID, we still have some oscillation. Now, if I consider a well with a really strong orientation, almost horizontal, you can see that the Z-torque does not work anymore. You have really strong oscillation, and the torque does not make any sense. So, of course, these are simulated data. If you add the feed-forward component, it's much better, but you still have strong oscillation, which might not be really good. Of course, you can filter the data and improve performance. This is just to give a general overview of the main ideas behind the different techniques. For the two other approaches, you can see that ID does not present strong oscillation, but the performance is not perfect. And recursive algorithm is really good, except that you have really high instantaneous torque. So to summarize the advantages and the requirements of different algorithms, the Z-torque plus feed-forward is really easy to implement because basically it's just Z-torque plus an additional component, but it does not require any additional measurements or huge computation. So it's a really low computational effort, a simple control architecture, and it presents good performance, except when you have really strong deviations. The MID can be much better, but it's sensitive to noise, and it presents a slight overshoot. Finally, the recursive procedure presents excellent performance in simulation, but it has a high computational effort and high instantaneous torque with a complex control architecture. So, of course, this is just a preliminary work, and additional comparisons need to be done. For instance, maybe we can use some model reduction techniques to improve to reduce the computational effort of the recursive procedure. Because it requires, for instance, the observer, so it requires solving in real time a partial differential equation, which can be time consuming, whereas that the V-torque is basically an improved PID controller, so it does not require having an observer that you need to solve in real time. So there is still plenty of work to do. Okay, Roman, do I have time to talk about that, or am I running out of time?
You're running close to time, but what we can also do is I can keep this meeting open later past the bottom of the hour, so if people have questions.
Okay, so I'm just going to be really fast on that, and if you have questions, we can discuss later, just to present briefly the results we have, because for the moment we have just considered the case of drilling device which is off bottom, and so but when you are drilling, at some point you have an interaction with a rock. And so you have some bit rock interaction, which is a well-known phenomenon, and it's one other cause of stick slip in drilling. Basically, it changes the boundary condition you have at the bottom, and you have a new boundary conditions that depends on the VB, which is the actual velocity, on the angular velocity, and on some factors. So that depends on the blade you are using, and epsilon, which is rock intrinsic specific energy. So depends on the rock you are drilling. So you have some complex function, nonlinear functions, which have a similar effect as the inclusion we have seen before. So it adds something new in the observation part and on the control part. In particular, the bit-rock interaction, the torque on bit now is not equal to 0 because you are not off bottom. You have this interaction with two parameters, A1 and A2. And it's a kind of, it's a bit similar to the inclusion we have before, because you have two different cases. One, if the angular velocity at the bottom of the well is greater or smaller than a threshold, a given threshold. So you have a new expression for your boundary condition, but you can still somehow use the same observer as before, except that now you need to update the boundary condition in the observer Florent showed you, and use a similar kind of adaptive law to modify, to estimate in real time the coefficient A1 and A2. So basically, this is what we have done. Of course, you need to know the actual velocity, or in the next step, we hope to estimate it. The problem is that as the bit-rock interaction effect and the Coulomb effect have at the end, when you draw the plots, similar effects, although they are physically completely different on the measure output, they're non-distinguishable. So it means that you need first to estimate the side force friction factors mu kin and mu star when you are rotating off bottom. And once you know these factors, you can estimate the factors A1 and A2 I've just showed you to get the bit-rock interaction coefficients. So you have to do the estimation in 2 steps. Otherwise, the parameters are non-distinguishable and you won't be able to estimate them properly. So just to show you some simulations, this is what we obtain with bit-rock interaction for the torque. And so this is the ROP. You can see that after some time, we have the correct estimation of the torque. And the same holds for the angular velocity. So in the first part, when you don't have any when the ROP is equal to 0, you estimate the static and kinematic friction, and then you estimate A1 and A2. This is why you have a transient here, where the estimation is not good. So the estimation is good here because we assume that mu kin and mu star have been correctly identified. Here you have a transient, and finally the estimation becomes good again. Okay, and this is the estimation of A1 and A2 we have done in simulation. So these are results from 2018 or 19, but I think Roman obtained with Shanti some other results recently on this topic. Okay, so to conclude, to summarize the presentation, there are different two causes for stick slip. One is related to the regenerative effect in the bit-rock interaction. The other one corresponds to the velocity weakening of the side force. We have derived some models which are able to reproduce a different phenomenon, and we have proposed a real-time estimation procedures. If you are when the bit is off bottom, the estimation procedure correctly works, and it has been tested against field data. When you have a bit-rock interaction, unfortunately, the effect of bit-rock interaction and the side force effects are not distinguishable. So you have to perform the estimation in 2 steps. From a control point of view, you can reduce the stick slip by cancelling the reflection terms and using improved PI control laws at top torque and Z torque. But we have been able to derive specific control laws that have been derived for distributed parameter system that have some advantages in terms of performance, but have some drawbacks in terms of implementation and control effort. And so for them, we need to pursue further investigation. There are some open problems. First, the bit-rock interaction from a control perspective is a nonlinear effect, so it might be really difficult to derive a control for that. So we need to simplify it in the model to have something which is usable in practice. So we need a trade-off between the mathematical representation and the realistic bit-rock interaction. Some stability results we have for the control law at some point must be tested against field data. As the bit-rock interaction depends on the nature of the drilled rock, we have developed some seismic while drilling approach to estimate the nature of the rock while drilling, because otherwise you have another unknown parameter, which is the nature of the rock. And so one of our future goals is to predict occurrence, optimize operational parameters, and improve bit design. So as I said, the take-home message: 2 distinct causes of torsional stick slip. To be able to model these causes, it's interesting to use a distributed models to have a practical relevance instead of just finite dimensional systems, finite dimensional models. We have managed to design an adaptive state observer, but there are still some key modeling challenges. Bit-rock interaction is one. Of course, testing some control procedure against real field data on real systems. For the moment, we have only considered torsional oscillation, but you need to consider coupled actual torsional coupling, so having a bigger PDEs, and also to understand coupling to lateral vibrations. And regarding the control law, we have tried to present different controllers, but this control approach needs to be compared, validated against real data or real system. Thank you for your attention. So if you have any question, I'm pretty sure that Florent will be happy to answer them, or I can also answer some of them.
All right, so thank you both for that amazing presentation. So I do know it's the bottom of the hour, so if you have to take off, go for it. I'll record the next few questions, and then these all be posted. And also, please feel free to reach out directly to either Jean or Florent if you have additional questions and you do have to leave now. But with that, I'll open the floor to questions.
John and Florent, thank you very much. Unbelievable amount of detail in this 1-hour presentation. Just to let you know, guys know, you had about 44 people online for most of the presentation. I think a few have had to drop off now, but most are still here in fact as well. So that would be a pretty good crew, given that it's early morning some places in the world. So
Thank you.
I had a couple of questions. You made an assumption on a friction model, which is that that step type model when you transition from static to dynamic. Have you looked at the sensitivity of that model? I'm kind of, yeah, there we go. Thank you. I'm looking at that friction model versus others. You know, what made you decide that model, to use that model as opposed to a more, let's say, typical
one with Strebeck effect?
Yeah, Strebeck effects or anything else.
Okay, so actually Roman is by far the most qualified to answer this question. One thing I will say with this model is that it has a very limited number of parameters needed to describe it. And with the uncertainty that you have, like, you know, on the exact shape of the Strebeck curve, I would say, at least using it, one of the biggest benefit of using such a simple model is that you basically have 3 parameters to calibrate. So that's one advantage. Yeah, and the omega C here really helps you have good numerical performance, in the sense that you avoid a lot of, you know, jittering effects and so on.
Yeah, numerical instability. Yeah.
Yeah, exactly.
One of the guys online is one of our engineers, Rajat Dixit, and we've experienced that numerical instability ourselves. So I know exactly what you're talking about.
Yeah. Roman, do you have anything to add on that topic? Maybe.
Yeah, I think you nailed it on the head. So it's for simplicity of that estimation, because here, especially if you assume that the red line is flat, so it's horizontal, it's even easier to estimate. With the Strebeck curve, you have several parameters to estimate, plus it's also nonlinear. Simplification.
Yeah, and the reason I asked is I saw some high frequency content. I think it was slide 17 that your model showed, and I was wondering if that high frequency content, keep going, slide 17, I think. It would show that there too, but keep going. 17, go back 3. Oh,
it may have been slide 17 in your deck, Florent.
Oh, okay. I tell you what, it's the one where you're showing the actual torque versus the your computed torque. Let's go forward a couple. Let's see on this deck. One right there. There you go. So your model shows a you know, I'll call it a high frequency content that doesn't show up in the measured values. Possibly sensor, you know, damping or other things as well, but it also occurred to me that might be due to that I'll call it the switching effect when you're going from stick to slip kind of thing. You have a large jump in friction, right? And I didn't know if you had any thoughts on whether that was due to the model or whether that was due to something else.
That's an excellent question. I would. That's not from going to, from stick to. I mean. Okay, I would say my guess is that we used a very, very low viscous damping coefficient for this, and so you completely neglect the effects, you know, the damping along the drill string from just the drilling fluid typically, and I would say that's why all these high frequency things are still here when they don't show up on the sensor data.
Okay. Yep.
Yeah.
But you don't think that's a switching from static to the dynamic?
I was no, because it's much higher frequency than the actual stick slip, and I would assume that let me see how that's 1, 2, 3. That's 1 hertz, more or less. These high frequency stuff. Yeah, I'm actually not sure, but no, I don't think there's any numerical effects from that Coulomb friction, no.
Okay, all right. I have lots of other questions, but I'm gonna let I see Eric's hands up and a few others, I'm sure. So
yeah,
I'll let them
have
talk
to
first.
answer Peter's question, Fred's question about surface torque as well.
You answered it in the text. That's fine.
Okay.
Eric,
ahead,
I think, yep.
Yeah. Okay, Florent and Jean, thank you very much for a very good presentation. It was very nice.
Oh, hi, Eric. I didn't know you were here.
Yeah. I'm just wondering, so you focus very much on the rotational velocity, but what about the actual velocity? Because this is not dissociated phenomenon. In a way, the friction is acting against the combined effect of rotational and actual. So
do you mean off bottom, or even you mean even off bottom?
Even of especially off bottom in a way, because on bottom, so you have only the ROP as an actual velocity, but in the off bottom condition, you may have if you are rimming up or rimming down, so you have an actual velocity which will combine with the torsional velocity, and your friction force is well, in a very, very simple approximation, will be constant at any contact points, but will split between the actual velocity and the rotational velocity components.
Right. So what I would expect in that situation is that we will somehow see the changes on the kinematic and static friction estimates. So we will, let's say, incorrectly attributing the effect of velocity to these coefficients. In a way, I mean, what we've shown here is obviously only good for the assumptions that we've made. So I think this is an okay tool for the moment at a startup. So before you're moving.
So starting of the top drive out of bottom.
Yeah.
And especially the control that Jean has explained would be very well applicable for this. Yeah.
Right. But I completely agree with you. As soon as you start moving vertically one way or another, then this will deteriorate quite fast. And we're definitely looking for a way now to include actual dynamics, but in a way that still allows us to use some of the tools that we use here to design observers, right? So this level of simplified modeling is as soon as you start coupling actual and torsional becomes very difficult. Also because the sensors we have for actual motion are very slow compared to the actual motion, the actual motion. So yeah, this is a tough one.
But this coupling actually is quite important also to the generation of stick slips off bottom as well, because of,
even off bottom. Okay.
Yes, even off bottom. So you have pointed to one source of torsional oscillations, which is linked to the transition from static to kinetic friction. But there is another source, which is the coupling between axial and torsional when you are off bottom. And you can see actually from downhole measurements, when you are rimming up or rimming down, that torsional oscillation starts at the moment you change direction. And especially when you are rimming down, actually you can go in full stick slip. And that's a side effect of hydraulic, the surging pressure, which interact with the rest of the string.
Okay, so now you have to include not only actual and torsional, but also the hydraulics.
And another thing that you may also consider is even if you are rotating and not moving actually, you may have a rolling of the pipe on the side, and then it slides. And when you are rolling, you are in static friction conditions, and when you slide, you are in kinetic friction. So the lateral movement while you are rotating is actually influencing your results. But that's just for the next interesting topic. Yeah.
Next decade of research. Yeah, and from a mathematical point of view, if you add the actual dynamics, then you have a non-scalar equation because you have two actual plus torsional. We have obtained some in the absence of friction terms, so just for ODE, linear PDE, ODE systems, we have obtained recently some results to deal with interconnection. So a possible path to follow would be to adjust the kind of observer we have, the adaptive one, with these new observers we have derived for linear ODE, PDE, ODE. But one problem might be that the different coefficients might not be distinguishable. So as Florent said, we may have to do it in 4 steps to estimate one coefficient one after the previous one.
Yeah. So at least we have seen in practice that you have a different response depending on the rotational velocity for this. Well, not only the stick slip, but I think it is linked to this fact that you have the rolling effect, which is happening in some part of the string and not everywhere. So, but yeah, that's something you can.
But you know, another way to
consider.
I guess to respond is the static and kinematic friction terms that we estimate in a way are already a very heuristic description of what's happening.
Sure. Yeah, it's
and I think
global.
This is how they should be seen and used, in the sense that, I think there's probably some use to it for the the diagnosis or fault detection or things like that purposes, but quantitatively I'm unsure whether they give a lot of information. I mean, they give some information, but it needs some interpretation already.
And one final point before Zach can ask a question, that's how do you calculate the contact force? Do you account for the curvature in the well?
Yeah, absolutely. So there's a law, I don't have it here, but yeah, it's in
because there was nothing about how you calculate the contact force.
Yeah, sorry, I mentioned it, but it's sorry, Jean, can you go back up, please? No, sorry, it was down then. Yeah, after this, right after this. Yeah, so yeah, there's a no, sorry, here. Yeah, there's all these coefficients, rho R0, no, yeah, here. R0 and Fn, which depend among other things.
Okay.
On
yeah,
the
but Fn, yeah, you don't say
exactly.
how you calculate Fn, yeah.
Yeah, sorry, it's in Roman's paper, the original modeling paper, but yeah, it depends on the curvature.
Because we notice when we use a model that there is a lack of account for the curvature in the calculation for Fn.
Okay.
So actually the psi forces are completely wrong in kickoff parts. So
okay,
we need to talk.
I would say that's the main thing that plays a role in this equation. I mean,
yeah, but there is this capstan effect in a way in kickoff parts because of the curvature that needs to be accounted for the side forces.
Okay.
If you don't account for that, then you are underestimating Fn.
Okay, then maybe yeah, I understand what you mean. Then we don't take into account. I mean.
Yeah, I think.
I mean, we have a 1D model of the drill string,
you only
right?
take the inclination, the effect in inclination.
Right, the inclination. Sorry, yeah.
But not of the curvature.
Yeah.
Yeah, I was going to say I can't help. I noticed that one of the models, or one of the things you modeled, is a S-shaped curve. Build, hold, drop well, that
Yeah.
is notoriously difficult in terms of stick slip off bottom, because, and I think it's partially that curvature effect is the extra tension that you get in the string around those corners or the contact force. So I waved my hands and said that that's the case. I haven't actually tried to model it, but I think Eric is right on that too. I believe that's important.
So,
and I have plenty more, but I stop there. So thank you very much again, Florent and Jean.
Yeah, no problem. One thing about the use of observers is you kind of you can make up for some model mismatch thanks to the fact that you're just constantly feeding measurements to the system, right?
But can you use Laplace transform on nonlinear equations?
No, you cannot.
No, because you have a nonlinear equations when you have a mechanical friction. You end up
So
an
what
absolute
we do
value.
is, what we do is we linearize the equation just to design the way we inject the measurement, but then we inject the measurement on the nonlinear equation.
And how do you manage when you are close to the absolute value effect when you change the speed, the sign of the friction? It's not very easy to linearize it part.
No. So we linearize it around an equilibrium that is in the linear part, basically. But then when we use so that's only to compute the gains. Once we have the gains, then we use them on the nonlinear model.
Okay.
So where there's no need for linearization anymore. Yeah.
Okay. Zach, it's your turn. Sorry.
Thank you very much, Fred.
Thanks for the presentation. It's really interesting. I had a question about slide 35 in Jean's presentation. This was a slide where you were comparing soft torque and Z torque. I was wondering if you could tell us a little bit about this case. How did you, it looks like this is probably a test case that was designed to distinguish these methods.
Case that is from a paper written by Ulf and Roman and maybe Florent. I don't remember exactly if you are in this paper. Just I'm trying to find the paper. The inclination of the well for these two cases is different. Basically, one is almost vertical, if I remember correctly, while the other one is not. I'm just trying to find the paper at the same time, because maybe you remember, Florent, because I think you are one of the authors, or Roman.
Yeah, give me 1 sec.
I can just look up the paper if that speeds things up. I was just kind of wondering if there were things that you had put into this particular case to allow it to distinguish between these methods better.
It's a kind of it has been done on simulated data with strong inclinations for sure, but I don't remember exactly the parameters that have been chosen or the specific details, because I did not really work on this paper. It's just from plots I took from this contribution.
Okay. Yeah. All right.
Yeah. Sorry. I'm searching for the paper. I'll look it up in 1 second.
The link to the paper is in the chat. So for this specific one, what we did was we played with a inclined well, and then we made these pretty much the stickiness parameters for the long string friction, let's say better or worse. So I would say more of a smooth wellbore with sandstone, or more of a sticky wellbore with chalk.
Thanks.
Thanks, Roman.
I have a couple of questions, if I can. One of them is going to be real simple, and that is, have you done anything, and it's a follow-up with what Roman just said, have you done anything to estimate different friction factors along the length of the well? So are you assuming a uniform static, uniform dynamic, or we know that everything was drilling fine, we drill into some different formation, it appears, and let's say the BHA has got probably a different friction factor that's exposed to. Have you done anything with that, or estimating friction?
So far, we have assumed that the static and kinematic coefficients were uniform along the drill string. So
Okay.
Yeah, actually, we even lump most of the friction at the BHA, which which we know is untrue, but in the estimation procedure, we have to lump everything at 1 seagulls. But what we haven't tried to do was to change the location of where we assume that the friction is along the drill string.
Yep.
Yeah,
this is of specific interest when you have multi-sectional drilling device with different type of pipe, for instance, and in that case, of course, the analysis becomes much more involved because you have all these interconnected PDE systems. So it's
yeah. I didn't say it was easy. If it was easy, I'd have done it already. No, and admittedly, now you got so many parameters in your model, and you can make it fit anything. The reality is, can you measure what's important or not? So
right, exactly.
To see, but it seems, just, and I'm talking about drilling experience, it seems there's two things that I can be drilling, everything is fine, and I then go into a more difficult section of drilling, which can be the drill bit, but then it can even be off bottom. I still have that as sort of like and I've attributed it to, like Roman said, in the anhydrites and even some of the limestones that'll be more difficult in terms of stick slip than a shale or something like that, perhaps. So the other, now that was the easy question, by the way. The harder question is going to be, so the guys that sell me Z-torque kinds of systems used to, back in the first implementation, said I need a torque sensor below the top drive, and I need a speed sensor. Speed sensors are easy, we can get those, we can get easily enough. Torque sensors below the top drive have been more difficult and harder to come by and do well. So the current implementations that I've seen of Z-torque include now a speed sensor that's high, in theory, high enough resolution to get accelerations, and then use the top drive input torque as the other. Did you simulate that? And in other words, I know I'm already getting an approximation for the torque of at the top of the drill string when I do that. Did you simulate that, or what did you use for your boundaries up there?
I can go ahead and answer that one. So we assumed that we had a torque measurement we assumed we had a torque measurement at the drill pipe. And then we also had a motor inertia that we used so that we could subtract out motor, motor inertia torque. However, I agree with you. So the actual field implementation includes that filtering of your velocity term, or your velocity sensor, to give you a smoother acceleration. Plus, it has an estimator that gives you an estimate of pipe torque based on your motor torque, or your VFD torque that's being fed into the motor itself. So both of those controls, or both of those loops, are part of the shell system. And they aren't directly part of the model, because this model is more of an idealized Z-torque rather than the field Z-torque.
Right. Okay. Very good. Well, I haven't tried the real Z-torque or the idealized Z-torque just yet anyway, but I am interested to see if that's a good enough approximation for a controller to work well. So
yeah, idealized Z-torque works really well. The censored Z-torque also works pretty well, except there's a few tweaks you need to do with timings on filtering. I don't know how much I'm allowed to talk about that, because that's still technically Shell's property.
Fair enough. All right. Very good. Thank you.
Eric.
Yeah, I have a question for Jean. You mentioned in your controller that you are using a maximum torque or torque limiter for the when you have some high torque demand. Do you have a torque limiter which depends on the rotational velocity? Because in a normal top drive, in a way, so you will have a flat maximum torque when you are in current limiter mode of the VFD drive, and then it will be a kind of hyperbolic response when you are above this current limiter response because of the increased impedance when you have larger frequencies.
Yeah, no, we just use the constant one.
Okay.
Constant value.
Because I've seen quite a lot of torsional stick slips which comes from when you go to high frequency or high RPM, because the top drive cannot drive the Drillstring anymore in ERD wells.
That's actually relatively important for some of the things we do, because we have seen that going into higher RPM before converging back to your nominal value really helps. And so, but you're right, it requires like relatively high RPM and torque at the startup, and so this is definitely something that we should include.
Because I guess Paul knows everything about the ARD wells, but in the ARD wells you are really at the limit of the top drive, and then these limits of what the top drive can provide is really a very easy source of oscillations.
Yeah, I was going to say, I was just going to reinforce exactly what you said, that we in field examples over and over again see that we either reach a top drive torque limit and we start stalls, which feeds back into stick slip, and we try to make people aware of that, because there's no Z torque or anything else that will solve that problem if it's stalling the top drive. So yeah, I 100% agree with you on that.
And especially if the controller requests a very large acceleration, which will definitely blow up actually the limit of the top drive controller.
Yep, and I was going to say, we've seen the same on power requirements, even though we might not be at the top drive torque limit as far as the top drive machine itself. The generator set that we're running, if you had, let's say, 2 generators running instead of 3, we've seen stick slip come from that poorer level of control, if you will. So kind of it's just one more one more difficulty to have to deal with, but you know, it's good to at least be aware of it, because you see people trying to solve, you know, say, why didn't my Z torque work or soft speed or whatever, and the answer was because you completely overwhelmed it with something else. So anyway,
just thinking about what you said, Paul, about
calls for, sorry, real quickly, but that definitely calls for control strategies that explicitly take into account these limitations. So let's say, independently of all the modeling part that we've shown here today, you know, soft torque, Z torque are in a way, I will say with quotes, simple controllers, in the sense that they are linear controllers. Taking into account these saturations should definitely be a priority, I guess.
And I'd like to come back to what Paul said about the friction factors as a function of depth. And I was not agreeing with Paul when he said that. And then I thought, okay, yeah, maybe there are some cases where it's true. But experiments that we made with a tribometer shows that what is really mattering for the friction factor is a fluid, the mud, not so much the type of material. But this being said, there is the effect of the filter cake, which definitively depends on where you are. If you are in a porous, permeable formation, you may have a much larger filter cake. And maybe some research that you can go on, Jean and Florent, is what is the impact of time for your connection on your static friction evaluation when you have differential sticking, which is happening there, because your static friction will climb up to very, very large values the longer you have a delay for restarting the top drive after during your connection.
Okay, I feel like there was some misunderstanding about your question, Paul, earlier, and so the response that we gave. We do so. I thought you were asking if we were able to, or if you had tried to estimate at a given time different friction factors for different sections of the drill string, which we haven't. However, Roman has tried to identify friction factors for a single well, but at different depths. And he submitted a paper on this recently. So these are two different questions, right? So I think, Eric, you were talking about the second.
That's correct. Yeah.
Yeah, absolutely. So yeah, this is, but you haven't published it yet, Roman, right?
It's been published.
Oh, it's been published. Okay, I finished reviewing it.
Oh, geez, I'm gonna have to go read another paper that I haven't read yet. Goodness.
Yep. Well, because the beauty of this system is like if you do your friction estimation on, let's say, a one connection, so when you start rotating, but how often do you start rotating when you're drilling? Every connection. So you can then you can feasibly then have a friction estimate or a friction parameter estimate at every single stand, so that can give you a pretty cool evolution of friction along your wellbore.
Yep. Cool. I like it. I do like it.
All right, so it is 9:05 my time, so 10:05 Houston, and late o'clock for Jean and Florent.
5:05.
So I think what we'll do is, Jean and Florent, if you could put your emails into the chat. If anybody has additional questions, just feel free to drop them an email. I will also share their emails with everybody who's attending. But I think, thank you so much for taking some time out of your Monday morning or afternoon. And again, Jean and Florent, that was awesome. Thank you again. And we'll see everybody back in a month for our next incarnation of this technical seminar.
Thank you very much for having us, Roman.
Thank you for the
Thank you,
invitation.
everyone, for the discussions.
Yeah, thank you very much, both.